Marhaba. In this video, we will start learning different proof strategies and techniques which will be used to prove a broad variety of theorems. Recall that a theorem is a mathematical statement that was shown to be true by providing a proof. So we want to learn different strategies and techniques to write proofs. So to speak, so the aim of this of this video and maybe the next ones is to build an arsenal of proof techniques or proof strategies. Okay. Let's just recall quickly what is a proof. We introduced it in the last video. Okay, so what is a proof of a mathematical statement beta? Okay, so suppose we have a mathematical statement beta and we want to prove it is true, then we need to provide a proof. So, and what is a proof? It's a sequence of statements. Let's call the sequence alpha 1, this is the first statement, alpha 2, this is the second statement, and so on up to the last statement alpha m. So it's a finite sequence of statements. What is the property of this sequence is that the last one, the last statement alpha m is the theorem beta that we want to prove. It is the statement which we want to show it is true. Second, each one of them, so alpha 1, alpha 2, or in general alpha I, is either an axiom. We discussed what are axioms. Axioms are statements that we assume to be true, and we assume that we are working in domains where the axioms hold. For example, we studied the axioms of addition and multiplication, and one domain where they hold true is the real numbers, the domain of real numbers. So each alpha I is either an axiom or it is inferred by an inference rule from previous statements. So we can, for example, use alpha 1 and alpha 3 and deduce alpha I by a rule of inference, or alpha I itself could be a previous theorem. So if we prove theorems, we can use them in the proof of future theorems, or it could be a hypothesis. For example, if beta itself is a conditional statement, then we can use the hypothesis of this conditional statement. And recall that we don't write down the statements in this form. We write them in complete English sentences or any natural language. So we write proofs in our natural languages, and we write them in complete sentences separated by punctuation marks. When we finish a sentence, we finish it with a full stop. When we start a new sentence, we start the sentence with a capital letter. And at the end, we will have a clear, understandable paragraph or clear paragraphs. So we can imagine like mathematical proofs should be written in clear language, organized in a nice way. So in the same way we write literature, here we will write mathematical proofs. So this is what is a mathematical proof, the notion of a proof in mathematics. And now we will start learning different techniques of proving theorems. So let's start with the first technique. And what is the idea? The idea is that we need to understand the statement that we want to prove to begin with, and then we start thinking about its proof. So it's important to understand the logical structure of the statement that we want to prove. Let me illustrate. So the first technique we will use is to prove universal statements. So what are universal statements? These are, statements in predicate logic, which we apply the universal quantifier to. So in general, the form of a universal statement is the following. For every element in the domain, this element has the property P. So remember, this is the statement which says for every x in the domain. Remember, in predicate logic, we have domains for the variables from which we pick the values. For every x in the domain, x has property p. So suppose we want to prove this statement. Okay, so we want to show that this statement is true. Well, what is the strategy here? The first step is we choose an arbitrary element, say A in the domain. A in the domain. And what do I mean by arbitrary? I mean this element A, all what we know about it is that it belongs to the domain. It's a member of the domain, and that's it. We don't know if it's, say, even or odd. We don't know if it's positive or negative. We don't know if it's rational or not, a rational number or not. We don't know if it's we don't use any properties of it other than being a member of the domain. That's it. And second, we use what we are allowed to use in proofs. So we use axioms, we use rules of inference, okay, we use previous theorems, previously proved theorems, or any hypothesis you have. And then we use all of this to show that A has property P. In other words, we show that P of A holds, is true. Okay. And now we finish by concluding, since we chose an arbitrary element in the domain and we showed, suppose we managed to show that it has the property P, then we can use one of rules of inferences, which is called universal generalization, to conclude that. So use universal generalization to conclude that every element in the domain has the property P. So to conclude that for all x, P of x is true. Okay, so this is the strategy of proving a universal statement. Again, so simply we choose an arbitrary element in the domain. We use what we are allowed to use, axioms, rules of inference, previous theorems. We show that this element A that we chose arbitrarily has the property P. Once we do this, then we know that every element in the domain has the property P, which means the statement for all x, P of x, is a true statement. Okay. Similarly, to prove that the statement, say, so to prove that, say, a statement with two universal quantifiers, say for every x, for every y, q of xy is true. Okay, so this statement says choose any element you want x in the domain and any element y in the domain, then the pair xy has property q. To prove this, we follow the same strategy. We choose arbitrary element A. So choose arbitrary. Okay. Choose arbitrary elements A and B in the domain, and then use the axioms, previous theorems, rules of inference, and then you show that the pair AB has the property Q. So show that QAB is true. And once we show this, it means that we managed to prove our desired statement. So if we choose arbitrary elements A and B and we show the pair AB has property Q, this means that for every x, for every y, Q of xy is a true statement. Okay. Sometimes the property on which we apply the quantifier is a conditional statement. So it has the form, say, for every x, the property is P of X implies Q of X. So this says choose any element in the domain. If X has property P, then X has property Q. So again, what is to take care of the quantifier, we choose arbitrary element A in the domain, and then we use axioms, previous theorems, rules of inference. Then we need to show, so we need to show that the property between brackets, this property, the green property, is true for this element A, which means that we need to show that P of A implies Q of A is a true statement, that this conditional statement has a true value. Okay, so you see, now we will discuss very soon how to tackle conditional statements, how to prove conditional statements. So we need to talk about the proof of conditional statements. And now let me say one more comment about universal statements. Sometimes common practice in mathematics that we write universal statements without writing down the universal quantifiers. So sometimes we just drop the universal quantifiers. So for example, you are familiar with the factorization of the difference between two squares. So we write when x and y are variables from the real numbers, we write that x squared minus y squared is equal to x plus y times x minus y. So we know this statement, but what we actually mean is this, that for every x, for every y, the difference between the squares of x and y is equal to their sum times their difference. Okay, this is a theorem. And I'll leave it for you as an exercise to prove it. So now how would you prove this? You need to choose arbitrary element x and arbitrary element y and prove this equality. And how would you here you will use the axioms about addition and multiplication. So we will prove now a different theorem about real numbers. So let's do it together. So here, theorem. We will prove that for every real number x, we have that x times 0 is equal to 0. Okay, this is a very common trivial fact. We know that when we multiply any real number with 0, we get 0. But we want to prove this. So this is the statement that we want to prove. Okay, here is the statement. And remember, what is a theorem? It's a statement that we provide a proof for, showing it's a true statement. So how would we prove such a theorem? Well, the first thing is understand the theorem itself. We want to understand its logical structure. It says for every real number x, when the multiplication of x with 0 is 0. So let's try to write this in predicate logic. So what is the logical form here of this sentence? It says for every x, where x is a variable whose domain is all real numbers, any x you choose in the domain of real numbers has the following property: x times 0 is equal to 0. Okay, so this is very similar to what we saw above. So for all x, p of x, okay, where the property p is multiplying. So x has property p. If when you multiply it by 0, you get 0. So this is the property p. Okay, so this is what we want to show, is that every element has this property, that when you choose any element in the domain and you multiply it by 0, you get 0. So let's start the proof. We write here proof and then dot, and then we start. Okay, let's start. how would we take care of the universal quantifier? By choosing an arbitrary element in the domain of real numbers. So choose any arbitrary real number and let's call it x. So we chose x. Now all what we can use about x is that it's a real number. It's an element of the real number line. Okay. So it's any point on this line. So it could be this is x. Any point to choose. All this is what we know about x. Okay. Now we need to use to write statements like a sequence of a proof is a sequence of statements. So we need to start writing the proof using what we are allowed to use. So we are allowed to use the axioms, previous theorems, rules of inference, and so on. So we will use the axioms about addition and multiplication of real numbers. So we will start by using the additive identity axiom applied by 0. The additive identity says that if we add any number to 0, we get the same number. So apply this axiom to the 0 itself. So it says if we add 0 to 0, we get 0. So by the additive identity axiom, we know that x plus, sorry, the additive identity axiom says if you have any real number x and you add it to 0, you get x. Now apply this axiom to 0 itself. Sorry, here I shouldn't use x because I already used it. So let me say it again. If you choose any number y and you add 0 to y, you get y. Now apply this axiom to the number 0. So what do we get? We get 0 plus 0 is equal to 0. Okay, so we know this. We know that 0 plus 0 is equal to 0 by the additive identity axiom. Now, let's see that x times 0 is equal to x times, but we know 0 is 0 plus 0. This is by the additive identity axiom. Now we use the distributivity axiom to distribute this multiplication over this addition. So we will distribute this x over the 0 plus 0. So by distributivity, what do we get? That the left-hand side is x times 0, the right-hand side will be x times 0 plus x times 0. Okay, now we will use the additive inverse axiom. So let me write it here. By the additive inverse axiom. Okay, what does it say? The additive inverse, it says every real number has an additive inverse, or every element in the domain where the axiom holds has an additive inverse. We apply this axiom to the number x times 0. Okay, so to this number. Look, we don't know yet what is this number. We know it's a number, x times 0. We want to show it is 0, but we still don't know what is it. So this is a number in the real number line. It has an additive inverse. So by the additive inverse axiom, let's say the number b be the additive inverse of x times 0. So let it be such that if we add it to x, this is a number and b is its additive inverse. So if we add b to it, we get 0. So now we add b to both sides of this equation of star. So add b to both sides. So what do we get? We get x times 0 plus b is equal to x times 0 plus x times 0. So this is the right-hand side plus b. We added b to both sides. Now we can use the additive associativity axiom, which says if when we add three real numbers, it doesn't matter which two we add first. So instead of adding the first two on the right, we can add, so instead of adding these two first, we can add these two first. Okay, so this is by associativity of addition. We can add these. So this is plus, and we can add these two first. Now, by choice of B, what do we know about B? B was the additive inverse of x times 0. So this is the left-hand side is 0 because B was chosen to be the additive inverse of x times 0. And this is x times 0 plus, and similarly here, we know that B is the additive inverse of x times 0. So this is 0. So here we get 0. And finally, by the additive identity axiom, okay, what do we know? That if we add 0 to any number, we get that number. We get that 0, the left-hand side, is equal to the right-hand side, which is x times 0. Okay. If we add 0 to x times 0, we get x times 0. And this is the required. So we proved that x times 0 is equal to 0. We can put a full stop here and say the proof is complete. And finish with a black square, say. Okay. So see, this is our proof of the theorem, which says if you have any real number x, then the product of x with 0 is 0. Okay. So notice that this is a universal statement of the form for all xp of x. We proved that every real number has the property that its product with 0 is 0. And all what we used here is the axioms about addition and multiplication, and of course we used mod exponents here without mentioning, okay, and maybe other rules of inference. Okay. So next we want to continue to describe how would we prove a conditional statements. And the first technique of proving a conditional statement of the form P implies Q is called a direct proof. Okay, so now direct proofs. Direct proofs of conditional statements of the form P implies Q, where P and Q are any statements. So what is the idea here? What is the strategy? What is the direct proof strategy? Okay, recall that. Okay, so recall that we discussed before that we can show that P implies Q is a tautology or is always true if we show whenever P is true, the hypothesis P is true, it follows that the conclusion Q must be true. Okay, maybe let me say it in a different way. That we discussed earlier that P implies Q is always true if we show whenever P is true, then Q must be true as well. Then Q must be true. And this is the direct proof strategy. This is how we will prove a conditional statement is true, by assuming the hypothesis is true and then show that Q must be true. Let me say quickly why this strategy does the job. Well, because remember, we want to show that this statement is true. This conditional statement is true. Recall what is the true, what was the truth table of this? It was true. It was false only in one case, when P is true and Q is false. Now let's show that it is always, let me convince you that if we do this, then we get a true statement always. Look at P. P is a statement. It could be true or false. If it were false, then the whole thing is true. So we don't need to worry, because when we define the truth table of a conditional statement, the whole statement, the conditional statement was true when the hypothesis is false. Now, so when P is false, the whole thing is true. It remains to see what happens when P is true. But when P is true, we suppose we showed that when P is true, Q must be true. So when P is true, Q will follow to be true, and so true implies true is true. Okay, another way to see it is that when we show this, when P is true, Q is must be true as well. We avoid the only case where it is false. So which is when P is true, Q is false. Okay, this case can't happen if we show that when P is true, Q is true as well. It follows that Q is true. Okay, so let me describe quickly what is direct proof. So to prove P implies a statement of the form P implies Q is true, like is always true, we do the following. One, assume, like we start by assuming that the hypothesis P is true. Next, we use what we are allowed to use. We use axioms, we use previous theorems, we use rules of inference. Until we show that, then we show, our goal is to show that the conclusion Q is true. If we do this, I mean, if you assume P is true, and then you show that Q is true as well, then we can conclude that P implies Q is a true statement. So this is the direct proof strategy. Assume the hypothesis to be true, show the conclusion must be true. So let's take an examples of using the direct proof strategy to prove conditional statements. But before we do this, I need to give you like some definitions about the integers. So recall what is an integer. So an integer is a whole number. The collection of all whole numbers or all integers is denoted by the letter Z. So what is Z? It is the set of all integers. We have the negative integers, 0, and the positive integers. So this is the set Z, the set of all integers, negative integers, positive integers, and the 0 integer. And we use the letter Z because in German, numbers means Zahlen. So let me write it here. This is the German word for numbers. It's a plural word. Okay. Now, so this will be our domain in the coming examples. Now, I want to give you some properties about integers. So we call an integer n even. So an integer, choose any integer in the domain, call it n, is even, is called even. So this is if there exists an integer k. Okay, so if there exists an integer k such that n is equal to 2k. Okay, so let me explain again. I am giving a definition. I'm defining a new term. This new term is named even. We choose an integer from the domain, choose any whole number. We will call it even if, look, this is an existential quantifier. If there exists an integer k. So if there is an integer, if we manage to find an integer k such that when we multiply k by 2, we get n. Okay. If we manage to find this k, then we call n an even integer. So let's try to write it in predicate logic. So n is, let me choose a different color. Okay, so an integer n is even if there exists k, where k is a variable whose domain is the integer. So if there exists an integer k such that n is equal to 2k. Okay. So this is the term even. Again, n is even if we can go to the domain of the integers, which is this one. Here is the domain of integers. And we can find an integer k such that when we multiply it by 2, we get n. If we manage to find k, then n is even. So when n, what does it mean for n not to be even? It means that such a k doesn't exist. So no matter how we try to find k whose twice k is never equal to n. So it means n is not even, means there exists no k such that, no integer k such that 2 times k is n. So if you go to the integers one by one and you multiply them by 2, you will never get n. In this case, it's not even. If you manage to find 1k such that 2k is equal to n, we call n even. Okay, now what does it mean for n to be odd? So now choose an integer n is called odd if there exists an integer k. Okay, so see here, we want to find an integer k such that n is equal to twice k plus 1. So what does this mean? We call an integer odd if we go to the world of the integers, to the domain of the integers. And we find one integer, at least one integer k, such that 2 times k plus 1 is n. And this is, in this case, we call n odd. Okay, so examples. Why 8 is even? So 8 is even because we can find an integer k such that 2k is 8 and this k is 4. So this is the integer k that we found. Okay, if we multiply 4 by 2, we get 8, so 8 is even. Now, why 11 is odd? So 11 is odd. How to show an integer is odd? You need to find a k such that 2 times k plus 1 is 11. And this k is 5. So 2 times 5 plus 1 is 11. And this is the k we were looking for. Okay, this shows it is odd. Okay, so, and what does it mean that an integer is not odd? It means that we can't find an integer k such that 2 times k plus 1 is. Okay, now I'll exercise. Show that an integer which is not even Not even means we cannot find k such that 2k is equal to the integer. Then this integer is odd. It is odd. And vice versa, and show that an integer which is not odd, it is even. Let me give you another property of the integers. So now an integer, another definition, an integer n is called a perfect square. Okay. When do we call an integer a perfect square? If there is an integer k, if we can find some integer k, so if there exists an integer k such that this n is equal to the square of k. Okay. So in predicate logic, n is a perfect square if the following statement is true. There exists a k such that n is equal to the square of k. So remember, what does this mean? It means when you go to the world of the integers, so when you go to this world, you can find k such that the square of k is n. So for example, why 1 is a perfect square? Because we can find the k such that the square of k is 1, namely it is itself. Okay, so we found this k, it is this k. We found 1 squared is equal to 1. Now why 4 is a perfect square? Because we can find the k, which is here, it is 2 squared. Okay, so here is, we found the k, it is 2. 2 squared is 4, and so 4 is a perfect square. And what other examples of perfect squares? Say 9 is a perfect square because we can find the k. Say here it is 3, such that k squared or 3 squared is equal to 9. So 1, 4, and 9 are examples of perfect squares. And when an integer is not a perfect square, if you cannot find the k such that the square of k is equal to the integer. Okay, so now we are ready to prove a statement which has the form of a conditional statement. So theorem. Okay, let n be an integer. Okay, then if n is odd, then n squared is odd. Okay, so you see, we want to prove that if we choose any integer n, if it happened that n is odd, then its square will also be odd. Okay, so notice, let's analyze the logical form of this sentence. So what is it? It says for every n you choose, for every integer, here the domain of the variable is the set of all integers, whole numbers. If n is odd, so let's use the predicate, say d of n, which says n is odd. Remember, a predicate is a descriptive statement describing a variable which becomes a proposition when we substitute a value for the variable. Okay, so this says for every n, if n is odd, then n squared is odd. Okay. So this is the logical form of the statement that we want to prove. It starts with the universal quantifier. So this is a universal statement. And we want to show that for every n, an integer n we choose, if n is odd, then n squared is odd. And so we can start testing that every integer has this property. Okay, so let me say here is n, just quickly to get a sense of the statement. Here is n, here is d of n, here is d of n squared, and here is the property. Here is d of n implying d of n squared. Okay, now when n is 0, d of n, like 0 is odd, this is false. 0 squared is 0, and 0 is not odd, so this is false, and false implies false is true. Now let's choose 1. Okay, 1 is odd, so this is true. 1 squared is 1, and which is odd, so this is true, and true implies true is true. Okay, now let's choose 2, for example. 2 is odd is a false statement. 2 squared is 4, which is odd, it's a false statement. False implies false is true. And say -5. Okay, -5 is odd. Why -5 is odd? Because we can write it as 2 times -2, where -2 is an integer. Actually, -3 is the k plus 1. Right? We found an integer k, which is -3, such that -3 times 2, which is -6 plus 1, is -5. So -5 is odd. And so this is a true statement. Now -5 squared is 25, which is odd, and true implies true is true. So this is what the statement is saying. If you choose any n, this property will always be true. So this is what we want to prove. Let's start writing the proof. So proof. Now we start by taking care of the universal quantifier. We want to show for every n such some property holds. So how do we take care of the universal quantifier? By choosing an arbitrary element in the domain. Our domain here is the domain of integers. So choose an arbitrary integer n. And now we need to prove that this conditional statement holds for n. We just discussed the direct proof of a conditional statement. We assume the hypothesis, and we need to show the conclusion. So what is the hypothesis? It is the green one here, which let me show. This is the hypothesis, n is odd, and this is the conclusion, n squared is odd. So we assume n is odd. Okay. Okay, now, and suppose, so, and choose an arbitrary integer n, and, or we can just finish this sentence with a full stop and start a new sentence by saying, suppose the hypothesis is true. So suppose n is odd. Now our goal is to show that the square of n is odd. This is the conclusion. Now, by the definition of odd, what does it mean to be odd? By definition of odd, we know that there exists an integer k. So there is some integer, we don't know it, but we know it exists, some integer k such that n is equal to 2 times k plus 1. This is the meaning of being odd. This is from our assumption that the hypothesis is true, right? We assumed, okay, it's green. we assumed n is odd. This means that n is of this form, where k is an integer. This is important. Okay, now we want to show that k squared is odd, n squared is odd. So now, see how we finish our sentence with the full stop. We start a new sentence with a capital letter. Now we have that n squared is equal to 2k plus 1 all squared, and this is equal to 4k squared plus 4k plus 1. Of course, to do this square, we used the distributivity property of multiplication and the associativity. We used many axioms about the multiplication and addition, but we skipped these in our mathematical proofs. Okay, now we can take 2 as a common factor of the first two terms. So I can take 2 and write here 2k squared plus 2k all plus 1. Okay, now I can call this number m, and you see that m is an integer. So let me highlight it here. So this integer, this object is an integer. Why? Because k is an integer. See, since k is an integer, then 2 times k squared plus 2k is also an integer. Okay, so this means that this is of the form 2m plus 1, where m is equal to 2k squared plus 2k, an integer. Okay, so what we see here, we managed to write, n squared in the form of 2 times an integer plus 1. Okay, any integer of the form 2 times an integer plus 1 is an odd integer. So this means that n squared is odd. So overall, what happened? We assumed that n is odd, and n is odd is the hypothesis, and we proved that n squared is odd. We showed that the conclusion follows to be true using our assumption that the hypothesis is true. Okay, so we can write the proof is complete and finish our proof with the black square. Or sometimes you can use an empty square, or you can use QED. There are several ways to indicate the finish of the proof. Okay, now what is an easy corollary of this theorem? So let me just put the theorem in a red box. Okay, so we proved this. So we proved for any integer n, if n is odd, then n squared is odd, if you want. So let n be an integer. If n is odd, then n squared is odd. An easy corollary, like an easy consequence of this, is its contrapositive. The contrapositive, recall that. So let me recall that P implies Q is logically equivalent to its contrapositive, which is not Q, implying not P. Okay. So if we call this P, if the hypothesis is P and the conclusion is Q, then since we proved this is true, okay, so we proved that this conditional statement is true, P implies Q is true, we know that its contrapositive is also true because it's logically equivalent to it. It has the same truth value. So let's write down the corollary. So corollary, let n be an integer, then the contrapositive is true. What is the contrapositive? Not Q implying not odd, not P. So what's not Q? N squared is not odd. but I asked in an exercise to show that not odd means even. So not Q, we know this is logically equivalent to not Q, implying not P. So not Q means n squared is not odd, which means n squared is even, implying not P, that n is not odd, n is even. So let's write it down here. If n squared is even, then n is even. So this is a true statement because it is an easy consequence. It's a corollary of the theorem we proved. What is the theorem? It says choose any integer you want n. If you know that the square of n is even, then it must be the case that n itself is even. So this is a second true statement we prove in this video. Now let's do another one. Another third theorem. It says, so theorem. Okay, let m and n be integers. So notice that this is a universal quantifier. For every m, for every n. If m and n are both perfect squares, so choose any arbitrary integers m and n. If you know that they are both perfect squares, then their product m times n is a perfect square. Okay, so what is the logical form here? For every m in the integer, so for every integer m, for every n, say p of n is a perfect square. So if p of m is perfect, and if m is a perfect square and n is a perfect square, so if we know these two pieces of information, that m is perfect square and n is a perfect square, then their product mn is a perfect square. So we want to, this is a universal statement with two quantifiers, a universal quantifier. So choose any m, choose any n. If they are both perfect squares, then their product is a perfect square. So let's prove this. What is the strategy here? To take care of the universal quantifiers, we choose arbitrary integers m and n. And now we need to prove that this conditional statement is true using a direct proof. What is the strategy here? We assume that the hypothesis is true, and then we show that it follows that the conclusion is true. Okay, so this is the strategy. Let's proceed. Okay, so proof. Okay, so choose any integers you want, m and n. Choose any integers m and n. Now assume the hypothesis. What is the hypothesis of the conditional statement? Assume that m and n are perfect squares. And then what do we want to show? The conclusion is true. Show that their product is a perfect square. Okay, so let's do this. So now suppose that m and n are perfect squares. What does it mean that they are perfect squares? So by definition of perfect squares, there exists integers k and l, say, where m is the square of k, and n is the square of L. This is the definition of a perfect square. Now, look at the product of m and look at the product. So now m times n is equal to k squared times L squared. Okay. So k squared times L squared, but this is equal to k times L times L. And now by associativity of the product, we can multiply the middle ones first, and by the commutativity of product, we know this is equal to k times, so KL is equal to LK. And we can write this as, by associativity again, KL times KL, and this is equal to KL all squared. Now, look at k is an integer, right? Look from here, we have integers k and L. Both k and L are integers, so their product KL is an integer. Let's call it B. So KL is B, and this means that m times n is equal to B squared. By definition, if an integer is the square of an integer, we call the integer a perfect square. So mn is a perfect square. As desired, and we finish the proof. Okay, let's see what the overall picture is. We assumed that m and n are perfect squares, and we finished our proof by showing that their product is a perfect square. And this is the direct proof. You assume the hypothesis to be true. This is m and n are perfect squares. So this, we assume the hypothesis, and then we showed the conclusion that the product is a perfect square. So moral of the story, if m and n are integers and they are perfect squares, then their product is a perfect square. Let's take a quick example of this. So here is m, here is n. For example, 4 is a perfect square, 9 is a perfect square. Then what is the product? 4 times 9 is 36, which is a perfect square. Why 36 is a perfect square? Because there is a k such that when we square it, we get 36. And what is this k? It is 6. So 6 squared is 36. So we proved another statement for today, which says choose arbitrary integers m and n. If they are perfect squares, then their product is a perfect square. Okay.